Okay, I'm told that we have to start exactly at 4 o'clock, so if everybody would take their seats. I guess we have a vast audience out there on the web. So it is my pleasure to introduce Chris Carilli, our speaker for today. Chris graduated a PhD from MIT in 1989, working with Bernie Burke. He then came here on a CFA fellowship, but after 1 year, he left for greener pastures. But then 5 years later, he showed up as a staff.
Bring this up every time. Go on.
He showed up as a staff member in the high energy for another year, about 1995. But then he found his true love at the National Radio Astronomy Observatory, where he's been for over 20 years. He's now the chief scientist there. And he also has a 20% appointment at Cavendish Lab in the other Cambridge. So those who heard Chris at lunchtime know that one of his main passions is looking at molecular clouds and star formation at high redshift. And he's one of the principal architects of the science case for the square kilometer in this area. But today he's going to talk to us about the hydrogen Epoch Reionization array, Hera.
That's right. Hello? Good. Thanks, Jim. It's always a bit of a homecoming. Thanks for coming out. Guess it's been a little while since I've been here. And yeah, indeed, I'm going to talk about cosmic reionization and 21 centimeter cosmology. I should say I think this is an area that is fairly familiar to the community, or becoming so, over the last few years. But there is, and it's a very exciting area to be in, as we heard. Aaron E.W. over here, I think he's here, gave a nice lunch talk on this, and then I introduced quite a number of the concepts that I'm going to mention. And there is some of the language that we're using within this community that's fairly specific, and I apologize now, but it is important that we get this out into the community so people become familiar with the kind of language we're using in the data analysis. And it's a very exciting time to be in the field because what we're trying to do is study evolution of large-scale structure in the early universe through the 21 centimeter line of neutral hydrogen. And the most basic measurement has yet to be made, and that is discovery of the signal, kind of like early days in even pre-Penzias and Wilson, right? So that's very exciting. We've got this target to go for. Now, what's not so exciting about it for this talk is that I'm not going to end with some tremendous crescendo saying we got this brilliant discovery. Wait a couple of years and, hopefully so. So you might say the operative word for this talk is progress. Progress is a good word. I like that word. Right, and I'm going to point out that there's been progress on 3 levels. I'm going to put the whole thing in the context of the hydrogen Epoch of Reionization array, which is a large experiment we're building in South Africa. And I'm going to start with a summary of the non-H1 21 centimeter measurements of the constraints on the evolution of the neutral gas in the early universe. Definitely some progress here. We're honing in on the redshift range for reionization, and also try to accentuate the fact that we really need the 21 centimeter measurements. It becomes more and more clear with time. As the measurements get better, we really need those measurements. I'm going to point out the progress in the measurements of the 21 centimeter line. Right. Excuse me. And we are actually making progress. They don't have a detection yet, but we are pushing down. We're fighting through the foregrounds, and we are making the first astrophysically relevant measurements. Like early days in the CMB, you might say. And then finally close with the progress on the Hera project itself. And I may not get to this later, so I should point out Hera is a broad collaboration being led out of Berkeley, lots of US institutions, some European institutions, and a whole lot of help from the South Africans. They have been a real big help. So start with a very schematic evolution of the universe. This is a little bit tiresome, but it's good to sort of folks who may not be familiar with this whole business at this stage is, the evolution of the universe, and in particular the hydrogen in the universe from the Big Bang to the present in a really schematic way. Starting with a hot Big Bang, the universe is hot, fully ionized, and the neutral fraction is essentially 0. few 100,000 years after the Big Bang, we expand, we cool, recombination. The microwave backgrounds then free stream through the universe, the relic photons from the Big Bang, through recombination. The universe drifts along in a essentially fully neutral state for some amount of time, maybe 1 billion years. And it's kind of boring, you might argue, but gravity's pulling things in, dark matter, the baryons themselves. Eventually the first stars form, the first black holes, the first galaxies, and these reionize the gas in the intergalactic medium, leading to a fully ionized gas between galaxies that we see today. Now, we certainly know a whole lot about large-scale structure formation at the epoch of recombination, right? And that's the microwave background, and we know this stuff to death now. The primordial structure, the temperature imprint of the primordial structure, the seeds for cluster formation in the early universe, as seen through imaging of the cosmic microwave background. We also know a whole lot about late-time structure formation through, the realm of the galaxies, through deep fields with the Space Telescope or VLA, or through very wide area surveys like Sloan. Now, it's this intermediate phase between, recombination and reionization, the dark ages through reionization, that one might argue is kind of the last blank space in our map, the area that we really have not mapped down in space-time. You might call it the last phase or the last frontier of studies of cosmic structure formation. It is critical because it sets that benchmark. When did the first stars, the first black holes, the first galaxies form? I'm not going to talk about that today. I'm really just going to focus on the simplest diagnostic, which is the evolution of the neutral gas. When did the gas reionize? How fast did that occur? And in particular, how can we study it using the 21 centimeter line of neutral hydrogen? So, sometimes it's good. I'll stop. Can I do that? Yeah. I'll stop this for now. Sometimes it's good to have a visual impression of the physical phenomenon you're thinking about. So this is a large-scale numerical simulation of cosmic reionization, galaxies forming on a very large scale, one co-moving gigaparsec. Numerical simulation now, so take it for what it's worth. But you'll see, the universe starts filled with neutral gas, right? So it's not an intergalactic medium; it's just space and time. But eventually, the first galaxies start forming. Large structures, clusters of galaxies. They emit photons. These photons reionize the gas in between galaxies. It starts slowly. Eventually, these galaxy formation is accelerating. The bubbles eventually overlap. Photons are shared. It's called percolation. And eventually, you'll go through this, what you might call a cosmic phase transition. It's not, I guess it is a phase transition, where all the gas in between galaxies just gets burned out by the intergalactic UV radiation field. We'll follow through this to the end. It's almost done, I think. And you'll see this, and then a little bit left, and then zip. It's all burned away, and the only neutral hydrogen left is in galaxies. And that's the goal here, as I said. Build a large array of telescopes to actually do this three-dimensional imaging, this epoch when the universe basically was just filled with neutral hydrogen. It's kind of a beautiful concept. And we can do it in 3 dimensions. Frequency is going to be distance over very large cosmic volumes. I'll come back to that as the talk goes on. So what do we know about the evolution of the neutral gas in the universe? And I show here the latest compilation based on non-21 centimeter measurements of the neutral fraction versus redshift here, from redshift 6 out to some high value. Compilation by Gregg and Messinger just this year. Some black points here are some either upper limits or lower limits, or possibly even a measurement here based on the Lyman alpha line of neutral hydrogen, and I'll explain that in a minute. And then some broad region in here, sort of an upper limit based on the epoch of reionization, based on the microwave background, and I'll explain that briefly in a few minutes. And then there's this broad red swath in here, which is essentially the modeling that Gregg and Messinger do, is forward modeling using simulations of galaxy formation, what we think we know, to use the measurements and get the best fit likelihood for the evolution of the neutral gas, which is the fundamental quantity we're after here, right? And what you're seeing is the Lyman alpha measurements have a tendency to push things out, and the CMB measurements have a tendency to push reionization in, with the general point, and we are making progress. This is the progress in the non-21 centimeter measurements. The universe is likely mostly neutral beyond a redshift of 9. I think we know that now. and the universe is mostly ionized below a redshift of about 6, and I think we know that fairly well now. And that's a new statement, only in the last few years where we could really make that statement. So I thought I'd talk a little bit about some of these points just to give you a flavor for the non-21 centimeter measurements, and also to accentuate the idea that 21 centimeter is really important. And here's the first kind of indication that we are pushing into cosmic reionization, and that's the Gunn-Peterson effect. You know, the idea is if you look for neutral gas between galaxies in the nearby universe, or the lower Z universe, that's the Lyman alpha forest, right? You take a quasar redshift 0.1, here's the Lyman alpha emission line, you get these little clouds here, which are some neutral gas floating in intergalactic space. You push out in redshift, and you get a whole lot more clouds. And Sloan had, I think this is one of the most important results that came out of Sloan. Lyman alpha emission for quasars between redshift 5.7 and 6.4. And as you move out, you get less and less transmission until beyond redshift 6 or so, the universe really is opaque, right? You know, there's no light getting through in the range of the rest frame Lyman alpha. So what you can do is derive an effective opacity as a function of redshift, and this is, I think, based on the Sloan quasars, an analysis by George Becker, which shows this systematic rise, possible acceleration in the effective opacity. Now, there's a simple equation that relates the effective opacity to Lyman alpha to the neutral fraction, right, for a diffuse intergalactic medium. And that's what Gunn and Peterson showed a long time ago, 1960s. It's more complicated than that because there can be substructure. That's not really relevant today. And from this equation, you'll see that down in here, the neutral fraction is probably of order 10 to the minus 5. And as you push out to redshifts of 6, you get a lower limit of about 10 to the minus 4. Important point here, another important point I want to make, is that the relationship between tau and F is, there's a big factor here. So even if the neutral fraction for the intergalactic gas is 10 to the minus 4, the universe becomes opaque. So it's a phenomenon that saturates very late that saturates at very low neutral fractions. Okay, so it's really a late time probe of cosmic reionization. However, you can use this Lyman alpha line. I had thought it was tapped out, actually, based on that statement. But there are other ways to use the effect of the interneutral gas in between galaxies to derive the evolution of the overall neutral fraction. Here's one of the points on that plot. You can take a galaxy, let's say, to redshift 6.1, and you can observe, for instance, the carbon-2 line, fine structure line, 158 micron line, with ALMA, right? Here's the ALMA image in the carbon-2 line. That gives you the host galaxy redshift. Now, the Lyman alpha spectrum I show here. This is increasing frequency now, so the axis is actually reversed from the previous plots. So this is red and this is blue. And you only see the very red side of the Lyman alpha emission line from this galaxy. So the idea is that this is possibly obscuration by the intergalactic gas in Lyman alpha. So what people do is they look for the change in the demographics of galaxies in their Lyman alpha properties. And I show here two examples of that. Either you can do narrowband surveys to look for Lyman alpha emitting galaxies at different redshifts. And you see very clearly between redshift 5 and 5.7 and 7.3, there appears to be a dramatic drop-off here in the number density of Lyman alpha emitting galaxies. Similarly, you can look at the equivalent width of Lyman alpha, the line to continuum ratio, all right, and you see, again, a dramatic drop-off here for Lyman break-selected galaxies now at about a redshift of 7. If you take this at face value, Gregg and Messenger calculate, this implies a lower limit to the neutral fraction of about 40% at redshift 7, which is a big number. Now, the difficulty here is separating out galaxy evolution from evolution of the intergalactic gas. Maybe galaxies just do this as you get to the first galaxies. Okay, from the other end, these are pushing out. Now, pushing in is the microwave background. This is not my work, so I'm just going to summarize it in 2 slides. People should be familiar with this. The idea is you have these photons free streaming through the universe from recombination, and as they go through the ionized gas, let's say during reionization, they Thomson scatter, right? And that has two effects. First of all, it fuzzes out the amplitudes of the fluctuations of the microwave background. Sort of like putting frosted glass in a window, and you look outside and everything's kind of fuzzy, right? It's degenerate with sigma 8, essentially. Secondly, you can get a large-scale polarization signal, very large scale, due to scattering of the local quadrupole during reionization. And WMAP has made claims that they actually see this very large-scale polarization signal in the CMB polarized signal. Both of these give you an integral measure of the optical depth back to recombination. And to summarize sort of the results here in one slide, I show here the measured tau for electron scattering back to recombination as a function of time from starting with the original WMAP results and now the most recent Planck results. And as over time it has steadily marched down to now we're at about 6% opacity back to recombination. There's a simple relationship between a model, a very simple model in which you assume the universe reionizes at a given epoch, bink, it goes from neutral to the whole universe, bink. So there's a simple relationship, which is good enough for today, between that instantaneous redshift and this measured optical depth. Now that's important because what this means is as this marches down, the instantaneous redshift for reionization marches up. This marches down, Z instantaneous marches down, which then means the observed frequency for neutral hydrogen marches up. And that's actually good for anybody who does this stuff because working at lower frequencies is significantly harder than working at somewhat higher frequencies. And this is kind of the state of where we're at today in terms of the microwave background. Challenges here, it's a very large scale signal in the polarization at least, which is hard to extract given the current measurements. And again, it's an integral measure of the opacity back to recombination, which can be fit by many different physical models. Okay. So to return to this, this is kind of the current state of the art in terms of our knowledge of the evolution of the neutral fraction of the universe versus redshift. And you see again here this red swath, mostly neutral beyond redshift 9, mostly ionized below redshift 6, 50% neutral fraction, probably about a redshift of 7.5 or so. That's the red thing. This narrow yellow line here is what we would expect to get if we can make the measurements that we expect to make with the Hera telescope. This is actually fairly pessimistic, honestly. But if we can do the 21 centimeter cosmology accurately, and we hope to, we will actually get a very, very accurate measure of the evolution of the neutral fraction. So, there's progress, but there's a broad swath that's still allowed. And most importantly, as Greg and Messenger point out, unfortunately, no current observational set is sufficient to break degeneracies and constrain the physics of reionization, and that's really what we're after. Hence the 21 centimeter observations, kind of seeing through the fog back to the early universe. Again, typical range, redshift 6 maybe to 7, 8, 9, which puts you at low radio frequencies between 100 and 200 megahertz. Major advantages, it's a direct probe of the neutral gas. Okay, we're not inferring anything. We actually see emission from the neutral gas, optically thin emission. It's a spectral line, and this will become critical. So you get a full three-dimensional view of this evolution of structure in the universe. Again, keep that in mind. That is very important moving on. Low frequencies, so you can do very large cosmic volume searches, wide fractional bandwidths, very wide areas. And it's a weak transition, which generally speaking, it's a hyperfine transition, the spin-spin coupling. So it's very strongly forbidden. I think it has a lifetime of like 1 million years or something, or more, for spontaneous emission. But weak means that it avoids saturation. So the universe is translucent, it's not opaque. So this realization that we might be able to do this a decade ago, or maybe a little bit before that, has led to a real renaissance in what was a fairly moribund field of low-frequency radio astronomy. And I show here a couple of the examples of the telescopes that we're building. A lot of stuff on this slide. I want to make a few points here. This is the paper array in South Africa. Here's the MWA in Australia. They are dipole arrays. It's the kind of telescopes that you're not really used to looking at. There's no moving parts, for instance. And you can steer them electronically, if you like, by phasing up the electric signal from the different elements. And the fundamental measurement here, of course, is the cross-correlation of voltages between antennas or a given baseline. So when I use the word visibility, that's the power of the cross-correlated signal for the fringe on the spatial frequency on the sky that corresponds to the interference pattern between those two antennas. I'm not here to give a lesson in interferometry per se. But that is our basic measurement, is the cross-correlation of voltages between the antennas. So secondly, here are the main experiments working on reionization. I should say for Lincoln, there are some experiments that are pushing to lower frequencies into the dark ages, into the linear cosmology world, which is beautiful but very hard. And the LIDA project is trying to make progress there. These are reionization experiments, so higher frequency. I want to point out a few things there. A number of experiments taking very different approaches, either very wide area and wide spatial area but smaller collecting area, or small spatial area and a lot more square meters. The other important point here is these are all experiments that have been working for a few years, okay? And so, in fact, I'm going to be showing some of the latest measurements from at least the first 2 experiments here. Last point I really want, well, second last point I want to make here is that if you calculate what you expect to be the signal and noise in either a fairly pessimistic foreground removal scenario, which I'll explain, or an optimistic, even in the optimistic sense, these near-term experiments really don't expect to make very high signal and noise detections of the power spectrum of the 21 centimeter signal. We can get there, and we're hopeful, and we're pushing, but it's going to be a slog. Fortunately, we have certainly the Hera array coming along, which I'll describe in detail later, and then eventually possibly the SKA, well, actually the SKA-1 low will be built, approaching 10 to the 6 square meters in collecting area, and in these cases, we have a very good chance of making a high signal and noise characterization of the evolution of the neutral gas. So, a little bit of the physics here. Excuse me. And I will go through this in a little bit of detail. This is from a review article by John Pritchard and Avi Loeb here. And you'll see this becomes relevant later, so that's why I'm going to go into it in some detail now. I show here the relationship between the 21 centimeter opacity and the basic physical quantities, the density, contrast, the neutral fraction, and some interplay between the microwave background temperature and the excitation or the spin temperature of the gas that dictates the population of states for the 21 centimeter line. It's all just radiative transfer. Okay, it's straightforward. It's optically thin. I show here this is temperature versus redshift, increasing redshift or decreasing frequency for the 21 centimeter line. Microwave background, the kinetic temperature of the gas, and then the excitation temperature of the gas. I show here the brightness temperature, the mean brightness temperature of the sky from high redshift to low redshift in the 21 centimeter line, or surface brightness, if you like, ergs per second per centimeter squared per hertz per steradian. And then the ionization fraction, so neutral and ionized. Starting at high redshift, densities are high, meaning 200, redshift 200. The densities are high, there's some residual electrons, everything's bouncing around, and it's all thermal equilibrium. In that case, you'll see no signal for the 21 centimeter line because it's all in equilibrium with the microwave background. At some point, though, the density drops, the kinetic temperature decouples from the CMB temperature, and the gas actually cools adiabatically relative to the CMB. But there's still enough density to couple the excitation temperature, and you actually will get an absorption signal. This is at redshifts of 100 or so. And that's absorption against the microwave background, because it's cold. But at some point, the density drops even further. The excitation temperature recouples to the CMB temperature, and you lose your signal again. However, with the formation of the first stars, the colors really didn't come out here very well. It's probably for the best. At some point, the first stars, it's a very lurid plot. First stars, photons, Lyman alpha photons, they scatter about the intergalactic medium. They recouple the spin temperature and the kinetic temperature, but the gas is cold, and you get a strong absorption signal. And that turns out to be very important. People here are actually working on this theoretically. That turns out to be important. However, at the same time, galaxies form, X-rays from the first galaxies, shocks, various processes will warm up the gas. You get a weaker emission signal, and then eventually the gas reionizes, and the signal goes away. Keep that in mind as we move forward, okay? Because it makes the results semi-relevant at least. What is the end game for this whole study? And the end game is to actually do the three-dimensional imaging, to make the movie I showed earlier, right? Watch the evolution of the large-scale structure of the universe. And here's a calculation by Steve Frolinetto showing, what you might see with a vanilla model for ionization from redshifts 12 down to 6, where you just see the density field up here, mean brightness of about 20 millikelvin. Eventually, you get the bubbles starting with the galaxies forming, and then the neutral gas only in galaxies themselves. But you can work it out if you want to do this kind of imaging, direct imaging, even if you can fight your way through the foregrounds. You really need a full square kilometer array of collecting area. It's just a sensitivity, thermal noise argument. This is really the primary science driver for a full SKA low, right? However, we don't want to give up there, right? We want to make a detection. So much like early days in studying the cosmic microwave background, like Kobe, initially at least didn't make a map of the CMB, but they did see the statistical fluctuations, right? And that's what we're going to try to do, detect it in the power spectral domain, essentially variance versus wave number or inverse angular scale, large scales down here, small scales down here. We actually get a physical wave number here, H inverse megaparsecs, because of three-dimensional measurement, right, which is beautiful. So going from large scales to small scales here, you get a variance or in millikelvin squared. And this is a model by Matt McQuinn. What happened to it? Oh, it's hidden here. Fiducial reionization model for what we think we know about galaxy formation. This is the prediction of what the level of the signal we might expect to see and how it evolves. So starting at high redshift, you see basically just the density structure of the intergalactic of galaxies and gas in between galaxies, etc. But initially, the gas warms up and the signal drops, as I showed. But at some point, the bubbles kick in, and you get a characteristic bubble scale on a sort of 1 megaparsec scale, and the whole thing flattens out. And that turns out to be very important for the detectability for us. It rises up again during reionization. You get all this structure on megaparsec type co-moving scales, and then it goes away because the universe reionizes. All right, so those are things to keep in mind. You get this relatively flat power spectrum with a variance of about 20 millikelvin over a fairly broad range in wave number. Okay, what are the challenges to these measurements? One of the challenges is interference, and I just show one slide on this because I'm not so worried about interference right now. Originally, I was really concerned, but the way we mitigate it is simply by going to isolated places. Our experiments, Paper and Hera, are located some 600 kilometers north and east of Cape Town, up on the southern African plateau. And it's a pretty isolated region. And I show here waterfall plots. There's time versus frequency from 100 to 200 megahertz. And this is Greenbank, the US radio quiet zone. And this is the Karoo in South Africa, which is the South African designated radio quiet zone. And look, Greenbank isn't so bad, honestly. There's stuff, and you don't see the scale here, but Greenbank really isn't too bad. You can work there. But you've got everything from FM radio to broadcast television. This is probably a digital signal because it fills the 6 megahertz allocation, to satellites. And you can't get away from satellites. Here's Orbcom. And in fact, we use Orbcom as a satellite to calibrate our beam patterns. Here's the space station, I think, kicking in at some point in time. So right now, you'll see the data later. Right now, I don't think interference is our major challenge. It could change, but for now, I'm less concerned about that. This is the main challenge, the foregrounds. The sky is hot and confused at low frequencies, right? Here's an image at 408 megahertz of the whole sky, Effelsberg, and some maybe Parks. I don't know who did the southern part of the survey. And even in the coldest region, the brightness temperature of the sky, the surface brightness, is 250 Kelvin, which is, 10 to the 4 or 10 to the 5 times larger than the line signal that we expect. Okay, so we have a dynamic range issue. And the idea historically has been, well, this foreground continuum, either radio galaxies or our own galaxy, the diffuse stuff here, it's non-thermal emission, synchrotron radiation. Okay. Fundamentally featureless. So big, broad spectra over a very wide range in frequency. And our 100 megahertz observing band would just fit right in here. So the idea is, well, you just subtract out some very small, smooth function, and out falls your line signal. Aaron showed this morning, a schematic as well, right? So that's the goal, but you have to make sure that you don't couple in the continuum to the line signal through your instrumental response. And you have to do that at a very accurate level, 10 to the minus 5 or so, to 4 or 5. And just to presage the Hera array later, I mean, that's fundamental to the design, both of Paper and Hera, is to have a very broad response in frequency. As Jim, and radio astronomers can tell you, you just want to avoid standing waves on the antenna, which lead to resonances which could give you spectral structure on scales that is smaller than the type of bandwidths that you are going to analyze. 10 megahertz is about the limit of what we can analyze and not expect evolution in frequency. So you want to have structure that's much broader than 10 megahertz in your spectral passband. Sorry, I'm using jargon, but that's okay. And in that case, that dictates a 14-meter antenna, which will give you no structure smaller than about 20 megahertz in terms of the internal reflections of the antenna. However, you have to get the electronics right, and I talked to one of the students here that are also working on LIDA and trying to make the impedance matching work so you don't get standing waves in the electronics as well. Important stuff to make this measurement. But there is one challenge, and I wonder if you can see this. I certainly can. I like it. Yeah, that's all right. The point spread function, the synthesized beam of an interferometer is fundamentally chromatic, right? You understand that. You have an interferometer, you cross-correlate voltages, you get a fringe pattern on the sky which has a wavelength, which is roughly lambda over the baseline length, right? That is your Fourier component of the sky, your spatial frequency, from which you derive your image of the sky. And that depends on the wavelength or inverse on frequency, and then the baseline length. And I show an example here of that. This is an image of Cygnus A, of all things, in the northern sky with paper, and it's a cube going from 120 to 180 megahertz, so a series of channels. And you can watch this accordion effect, which the first time I watched this, it kind of freaked me out. Because if you think about it, if you want to remove the continuum, let's say in the image domain, and fit a smooth spectrum through this, you're going to get residuals as these side lobes wash across your position. And I show an example here, right, where, and that, the frequency of that standing wave, or whatever you want to call it, it's not a standing wave, but that spectral response is going to depend on the baseline length. Short baselines will have a big, broad response, big, wide side lobes. Long baselines will have a very sharp response in frequency. Okay? How do we get around that? This has become, and the reason why I'm dwelling on this, is this really has become the focus of the field for the last few years, is how to avoid the chromatic response of an interferometer. How do we get around this fundamental chromaticity? So I will dwell on this just for a few minutes. Again, it's a language thing. I'd like people to at least hear the language. Here's an image of the sky at 150 megahertz with the MWA over a large scale. There's two extremes. You can go through the full imaging approach, right? You find all these sources and you subtract them correctly from your measurements, right? It's hard. I'm not saying it's impossible. I hope it isn't. But you need very accurate calibration. And you also have to understand that at the short baselines and these wavelengths, the sky isn't just point sources. There's a lot of big, fuzzy, diffuse stuff out there that you've got to get rid of. So it's a hard problem. The other technique is avoidance, and I'll explain that in a minute. And fortunately, Aaron gave a nice introduction to this this morning. The wedge, focus on the line of sight power spectrum, and there's a natural region in that analysis for which the foregrounds are filtered out. So let me explain that in a little bit more detail. And again, this is a repeat from lunch, but that's good because it's an interesting concept. So you measure a power, a cross-correlation power of visibility, Jansky's, Kelvin, right, power on the sky. So you get a spectrum between 150 and 160 megahertz. So this is the fundamental measurement of the baseline, of the interferometric baseline. You get a spectrum, well, you know, frequency is distance, right? And you have some line signal, and then you have the broadband continuum signal. You Fourier transform that measurement, power, in frequency, right? So frequency is distance. You Fourier transform to the conjugate variable, which is delay, and that is inverse megaparsecs, which is wave number. And then you square that, and out falls your power spectrum against wave number. It's as simple as that. And in this case, what's also nice is that the line signal, having small scale structure, will extend to large wave number, or small scales, or large delays. It's all the same. The continuum, being very broadband, will pile up at small k, or small wave number, or small delays. So you get this natural filtering between the interferometric response to the continuum and the line signal. And I show here the current sort of standard analysis tool, which we saw at lunch today as well, which is known as the wedge. And these are real measurements now. This is line of sight wave number versus angular wave number, which you could call baseline length or inverse angle. And this is either delay or inverse frequency, which corresponds to line of sight wave number. Now, the color scale here are actually line of sight power spectra along a vertical axis, a vertical line here for a given baseline length. And I pull out some of them here for short baselines and long baselines. And what you'll see is the continuum emission piles up down here in this wedge-spaced region, right? And for short baselines, it's very isolated to small delays or small wave numbers. And long baseline, it pokes out to larger delays or larger wave numbers, right? And that is the wedge. And so the idea is you just don't work in here and you just look for your line signal out there. It's as simple as that. You lose signal noise, but there is this natural filtering of the foregrounds in this space. So you'll get these noise-limited spectra that poke out beyond the continuum. And that's basically, oh, you may ask, what sets this line? And Aaron described that this morning, and I'll just say it in words. It is the maximum delay in the system set by the length of the baseline projected to the horizon, or the horizon limit. So that sort of dictates the arrays that we're building. You can see this is a grid array, which is kind of a curious thing for most interferometers nowadays. You don't see these that often, except for like in the military. And so you have a whole lot of redundant spacings. And at any given time, you're making identical measurements of a given baseline. And, each one of these is exactly the same. It's got the same fringe in the sky. That's two important aspects to that. One is you can use a redundant spacing calibration technique to derive your complex gains, which I'm not going to describe, and it's useful. But more importantly, at any given time, you're making the exact same measurement of the sky, the exact same spectrum on the sky for a given spatial frequency, right? So that means you can add your spectra, in Jansky's before you square to make a power spectrum. If you think about that, that means that your signal noise increases linearly with the number of measurements and not as the square root as the number of measurements. And that turns out to be a really powerful technique in terms of building up your sensitivity. You add and square versus square and add. You add coherently is one way of looking at it. So let me just show you the process going through this. You start with this is from the paper 32 example, 32 elements. You start with a measured spectrum on a given baseline. You do the wedge filtering of the continuum, so it drops way down. You add up redundant spacing, so your noise drops down. You average in time, so you get a noise-limited spectrum down here that's fairly sensitive. You then pick out a chunk of 20 megahertz of spectrum. You multiply it by some window function to avoid the hard edges in your Fourier transform. You Fourier transform in frequency to delay space. You then cross-multiply, and out falls your power spectrum here, right? So that is basically the process we go through. And this is now millikelvin squared variance versus wave number. One point I want to make here is that in this particular instance, we were filtering, you see just this is the horizon limit, and we're filtering our foregrounds at the level of about 10 to the 6 in millikelvin squared. Okay, enough. How are we doing? Good. This is where we're at. The best measurement to date of the 21 centimeter signal from cosmic reionization is redshift 8.4, done by Carilli with the paper team. I show here millikelvin or squared versus variance versus a wave number here from about 0.1 to 0.6 inverse H inverse megaparsecs. A few points here. Again, we're getting wedge filtering here at this level. We're doing about 10 times better, about 10 to the 7 in millikelvin squared. So we're getting rid of the continuum fairly effectively just by using this wedge technique. The bluish line here is the noise power spectrum, what we expect just for noise based on our measured system temperature. And you can see we have a couple of points down outside the wedge, but well above our noise power spectrum. We're not exactly sure what that is. If you want to talk about that later, I'm happy to do so. But beyond about 0.2 in inverse H inverse megaparsecs, we have essentially a noise-limited power spectrum. And since we know the power spectrum during reionization should be fairly flat, we can essentially average these things up, and we get a number here, 360 millikelvin squared, right? And that is the current state of the art in terms of the 21 centimeter signal from reionization at a redshift of 8.4. Now we show here essentially that model that the Matt McQuinn model, or Messinger and Gregg, sort of a fiducial model for what we think we know about the evolution of the universe through cosmic reionization. And we expect, as I said, a signal in this range of about 20 millikelvin. So we got a ways to go. I'll admit that, right? We're factors of 20 or so away from a fiducial model for reionization. However, it's early enough in the field that we can start asking questions like early CMB measurements. Can we rule out what you might call non-fiducial but plausible models for galaxy evolution? And the answer is yes. We can actually start investigating parameters of early galaxy formation. And the parameter we look at is preheating of the intergalactic medium. And if there is no preheating, we expect a much stronger signal. Let me go back to that. I'm sorry I'm showing this plot twice. It's painful. But the point is this. We're in this regime in here, right, where the universe is warming up, and you're getting this emission signal down here of about 20 millikelvin. But the important point is that if for some reason the intergalactic medium never warms up before it reionizes, so it just sits there and it's cold, and it keeps getting colder and colder, right, this absorption trough will continue down, right, and you'll get a much stronger absorption signal against the microwave background, and then it reionizes. You still need the Lyman alpha photons, and that is actually a bit of a detail. But the important point is it's possible that the universe never heats up. There's no X-rays from early galaxies or something like that, or no shocks, in which case you might get a strong absorption signal. And people have modeled this. People here at Harvard have modeled this, Avi and his postdocs and students, et cetera. And I show here one example, and I don't remember where I got it from. And the frequency axis is reversed. So this is high redshift now, and this is low redshift. But the important point here is you have the predicted signal, absorption, and the strong emission in what you might call a fiducial model for the evolution of the intergalactic gas. But if it never warms up, and there are reasons to expect that it might not, you get a much stronger absorption signal. So Johnny Pobert did a very nice analysis of this. And he showed that given our measurement of 360 millikelvin squared, that the universe, it's degenerate with the neutral fraction, but for a reasonable range of the neutral fraction, the universe has to be warmer than about 10 Kelvin. The intergalactic medium has to be warmer in terms of the excitation temperature than 10 Kelvin, which would be the kinetic temperature too, which is actually a lot higher than what you would predict if there was no warming at all. So I think we can make a conclusion that the universe does warm up a little bit by redshift of 8 due to the first galaxies forming somehow. All right, so this is a summary of the current measurements, variance versus redshift now from the MWA GMRT paper. These are Josh Dillon's measurements up here. These are various paper team, Danny Jacobs, Aaron Parsons, and Zaki Ali limit down in here. This is for wave numbers between about 0.2 and 0.5 inverse megaparsecs. And, you know, the buzzword again is progress. We are making progress. We're pushing these limits down steadily, which is good. We're not hitting the fiducial model yet, so we still got a ways to go. But we certainly can argue that there is some early preheating of the intergalactic medium via galaxy formation. And most importantly, I think, you know, we're fighting our way through the foregrounds at this stage. We haven't quite hit any hard limit yet. So in the last 15 minutes or so, I thought maybe 10 minutes, explain the Hera project, which is the next step on this. We've got to push the sensitivity. We've got to push the capabilities of the array. And that's what we're doing. We're building an array in South Africa, which essentially has the collecting area of Arecibo with 450 times the field of view. Of course, only operating below 200 megahertz. 351 is the target eventually, 14-meter parabolic antennas operating from 50 to 250 megahertz in the radio quiet zone in South Africa. It's a collaboration, as I pointed out before, of the main reionization groups in the US, as well as some universities in Europe, and the South Africans really have been a tremendous help in all of this because we are in the SKA radio quiet zone. Building on the experience that I just described to you on techniques optimizing for a delay spectrum approach, but also, as I'll show, it should be a capable capable instrument for imaging large-scale structure, very large-scale structure. Go back to the antenna just for a second. The design really has been optimized both to get some forward gain. We need some sensitivity here. It's got 50 times the forward gain of the paper elements, but also to minimize spectral structure, standing waves, such that there's no structure in the response smaller than about 20 megahertz, which corresponds to a delay in technically of 50 nanoseconds. And here's a calculation of how this antenna performs. And hopefully it'll be pretty good. We're making the first measurements of the beam. It's about 8-degree field of view at about 150 megahertz, 70% efficiency, 65% efficiency, main beam efficiency. In terms of sensitivity, this is sort of what we expect for Johnny Pober calculation for the evolution of the power spectrum and what Hera might do if we have to work only in the wedge or outside of the wedge or in the reionization window, or if we can actually get rid of the foregrounds, the continuum. But in either case, you're getting a very accurate measurement of the evolution of the power spectrum of the neutral gas. This is one realization from redshift 8.5 to 10.5, doesn't matter. But you can convert that, as Greg and Messinger have done, to what this would infer for the evolution of the neutral fraction over this redshift range. And indeed, we should really nail that down if we can make this experiment work. And I think this is already in the pessimistic assumptions. So that is one thing that should fall out of these experiments, unless we really have no clue. Let's hope that's not the case. But you can go beyond that, and that's what Greg and Messinger have really focused on. You should probably get Andre or somebody to come here and give a talk on his work. It's very nice. To constrain the astrophysics of reionization. And what they've done is sort of like what you do in the CMB, the standard covariance. You build a parametrized model of galaxy formation, and then you try to constrain those parameters based on the measurements of the instrument. And so they've done that. They have a fast code for many realizations. It's a Bayesian forward modeling approach. Many realizations physically of the universe, reionization of the universe, with free parameters being the escape fraction from galaxies of UV ionizing photons, the mass limit for star-forming galaxies, and the mean free path of ionizing photons through the intergalactic medium. And indeed, according to their calculations, Hera should do a fairly good job of constraining the astrophysics of cosmic reionization, and that's good. And moreover, for CMB folks, if there's any here, we will help them as well. There is certainly, and they will tell you, a degeneracy between the amplitude of the fluctuations of the microwave background and the optical depth to the CMB measured, the Thompson scattering optical depth. As I mentioned earlier, this frosted glass in the window. And by measuring this, we will measure this accurately, and that will certainly help them constrain the amplitude of the clustering amplitude sigma 8. Now, if we can actually get through all the foregrounds, and I'm not completely pessimistic that we can't, we possibly could do imaging of very large-scale structures, 20 arc minutes. Now, this is big. But as I showed, that power spectrum is pretty flat. There is really big stuff during cosmic reionization, big bubbles. And we should be able to see those. The orange is a simulation of, from 21 cm fast of a very large area of the sky, is about 8 degrees across. And then the contours here are a simulation of what Hera might see in, I think, 100 hours. And of course, you get 3 dimensions. Each position here will have a spectrum. And we certainly could do a pretty good job of imaging large-scale structure if we can get through the foregrounds, as I said. And we'll get a swath on the sky of about 8 degrees across. It is a transit instrument. Okay, last few slides. The schedule. I mean, where are we at? We've been funded as of starting funding this October to at least build out to a very substantial array in the next 3 years of about 240 elements. Here is the state of the array right now. We're building out to 37 elements as we speak. I show here the sort of the Gantt chart, you might say. And the philosophy we have is build antennas and then observe with, let's say, 37, and then analyze the data, and in the same time keep building and at some point freeze the correlator and the electronics, observe for a season with 128, analyze the data, do science along the way, etc. So we're going to try to get limits out and hopefully a detection out as we move along in the next couple of years. And the important point is even at 37 elements, we have 14 times the collecting area of the paper array. So we're already at a level where we might stand a fighting chance of seeing something. And then at the end, we're done and move on to other things. And so let me, for the radio astronomers in here, I just want to show a couple of slides on data that's coming right off the Hera telescope itself. And it was just a few weeks ago, and it's always hard in these sort of deep experimental projects just to make the first basic sort of calibration and measurements. And so I realized that there's a lot of stuff in the sky, and we're having a hard time calibrating our data, basically. But it just so turns out that the galactic center, which is a strong radio source, this is 327 megahertz, I think, at sort of 20 arc minute resolution, I think, less than arc minute. Galactic center is a strong radio source, and it passes right through our beam once a day. Boop, boop. And so what I did was we took the galactic center and we used it as a calibrator, a sky calibrator, starting with a point source model and then iterating in a standard VLBI type hybrid mapping way. And I just show here some of the measurements. These are the measured band passes as a function of frequency for visibilities to one of the antennas. These are uncalibrated and these are calibrated visibilities. So these are the long baselines and these are the short baselines. This is probably real structure. This is fluctuations due to the sky itself. There's stuff on the sky. Point I want to make here is that you don't see a whole lot of missing spectrum, right? The spectra, at least for when there's a strong source in there always is. We just flag a couple of satellites, 6 different narrow frequency ranges. See one here, one over there, and then away we go. So interference is not killing us yet. Phases are a little bit more fun. And interferometry is all about phase. So again, for the experts, this is the uncalibrated phase, and you can see, Jim, what do we have in here? Delays. The delays are not calibrated. So you galactic center, you calibrate your delays, and you do a bandpass calibration. And again, the data is behaving very nicely, and the proof of the pudding, as Rick Perley says, is in the eating. So we can make a map. We make our first map, and you guys may not be very excited about it, but I certainly am. This is a big step. Right, once you can measure voltage and you make a map of the sky, and you can do almost anything. So here's our first map, low resolution. It's only 18 antennas. It's 10 minutes of data. Resolution of 1.2 degrees, and we're getting dynamic range of about 200, and we're seeing the galactic center and the galactic plane. This is where our primary beam, full width half max, would sit. Here is an actual image of the galactic plane in this. At this frequency, but at much higher spatial resolution, 20 arc minutes. And we're definitely, as I said, seeing the sky and able to make maps. We get and at each point we can get a spectrum, actually. So that's good. That's the whole point of the business. I would say something about grading lobes, but I won't because Lincoln's not here. He wanted to hear about that. So to conclude, if that's okay, again, the progress, the idea that we are making progress. We definitely, non-21 centimeter measurements are honing in on the redshift of reionization, and we're thinking now that 50% ionized intergalactic medium by volume between a redshift of 7 and 8. That's a big change from just 5 years ago, where this number was 14, right? So that's actually a really big change. And I think it's reliable, honestly. And I think I tried to accentuate the idea that we really do need the 21 centimeter measurements. Progress in the 21 centimeter measurements. We're exploiting the EOR window, we're fighting our way through the foregrounds, and we're making our first physically interesting limits to the signal, which suggests that the universe does preheat before it reionizes at a redshift of 8. And finally, Hera 37 is being built. We'll start observing in January, March. And we will continue to build out, and I'm sure you will be getting progress reports over the next couple of years. Here's some of our team down with the first 19 elements. So thanks, and I'm happy to take questions.
Thank you very much. Questions? Ready?
What troubles me about this development is that never mentioned is the fact that in exactly the redshift range as you're observing reionization, the universe is going through a second phase transition, which is the freezing out of the hydrogen. Remember that the freezing point, the triple point of hydrogen is 13.8 Kelvin, and the universe goes to that temperature at around this redshift range, somewhere probably between 7 and 9.
Freezing it into what? Molecular hydrogen?
No, solid hydrogen, probably coating ice grains or something.
Oh.
So it's disappearing from the map of the transmission of the universe. And second, the heat of fusion has to get radiated away at this temperature. And so it's filling the universe with a background of photons at the temperature of 13.8 Kelvin.
What are the densities you need to get it to freeze out at the dust grains?
The density of the temperature I quote, 13.8 Kelvin, is for near zero density. That's extremely high vacuum. And so
Would you need dust?
Sorry?
Do you need dust?
Who knows? There would be a phase change of the universe when you freeze out the hydrogen, and that should be the passage.
Well, this is going in the other direction. I would think that, our densities are low enough that one hydrogen atom is just not going to see another one for quite a long time, but we would have to work that out.
I think so.
Would that freezing out affect the optical depth of the CMBs when it gets in constraints?
Yeah, the A and B, we have measurements of the neutral fraction of these redshifts using quasar absorption lines, and as I showed in sort of probably too gory detail. And there's stuff, no question there's stuff.
Okay, the absorption line could be caused by the opacity of the hydrogen, gas or not. In other words, you would go from absorption spectrum to not absorption spectrum if the hydrogen has all disappeared because it's no longer gas.
It's hard. I'm just having a very hard time visualizing a single atom becoming a solid. It's kind of freaking out. But go on. Well, certainly single collisions might happen once in a while. Multiple collisions are probably zero. I'd say that would be one every n lifetimes of the universe. Yeah, Charles.
Well, actually, I had a very much more mundane question. Your antenna design, you have these parabolas for Hera.
Oh.
The paper, they just seem to be in trays. I mean, what
So there's a huge difference between the two. This is an antenna. The other one is a dipole. And I'll explain why that is. This has a backplane. I could go back, but let me not go back. These are actually paper dipoles in here, the feed itself. These.
It's a shield in the paper.
So in the paper, it's just a ground screen, and the dipole sees the sky directly. In this case, there's a backplane. We turn the paper antenna upside down, so there's a ground screen here, and the dipole's down there. So the antenna itself, the feed itself, only sees the antenna. So this is a real antenna. Paper is not. Paper is just a single dipole with a funny ground screen.
So this is the feed up here.
No, this is the backplane. The feed is there.
Oh, the backplane for the feed, right? The feed is there.
you can see it.
Right. So for the paper elements, there is no backplane. So the dipoles see the sky directly. Total different.
Okay. And how about LOFAR, which showed up in a couple of your slides? Because LOFAR is not in a radio quiet zone.
Oh, that's a different question. And I'm not going to jump on LOFAR, not at all. And what I'm going to say is that if you talk to the LOFAR folks, they claim that interference isn't a problem. They just sort of point blank say that. Is it rationalization? I don't think so. What they say is that a lot of Western Europe has just moved to higher frequencies. There's no bandwidth at low frequency.
And also in the difference between paper and Hera, we do see that a dipole on the ground, just being barely on the ground, makes a big difference. Where if you stick it 10 feet up in the air, you do actually see a lot more.
Yeah.
They're all on the ground.
Right. There's more interference with these because you're 14 meters up. Well, maybe 10 meters up, as opposed to paper, which is about this high. So, different approaches, not a bad. It's healthy.
terms of time frame, in one of the earliest slides, you had H331, which I assume meant 331
Yes.
elements. That was 2018.
Did I say that?
Schedule.
Well, did I actually? I don't know. That's an old slide. Did I say that? I don't know. Oh, no. That was sort of when Hera was. I didn't want to say that we're not going to get any results from Hera until 2021. We're going to be observing starting this year, so I could have put 2000, whatever it is, 17, but only 37 elements. So sorry, I had to.
I'm not very terrestrial in my questions. Does the ionosphere
Yes.
interfere at all?
Yeah. It's always a big question mark, isn't it? And I can give you just the short answer, which is here's the ionosphere, a beautiful view of the ionosphere at 74 megahertz with the VLA, an image of the Virgo cluster of galaxies. This is now at arc-second resolution using the VLA at low frequencies, and you can see the effect of the ionosphere as an ionospheric storm comes through, and it's a big, and there it goes. So yeah, that's like working through a thunderstorm. So yeah, the ionosphere is a problem with low frequencies. In our case, we have the one advantage compared to, let's say, LOFAR, is that the telescopes like LOFAR that use very long baselines to calibrate are actually seeing through different realizations of the ionosphere on like 50-kilometer scales. We have just very small, very short baselines, so we only see one realization of the ionosphere, and hopefully that will come out of the calibration. It's not trivial, but I don't think it's our biggest problem right now. We'll get there when we do.
I have a different question. What about the data rates and how this, you will get data, how this compares to alpha type of data volumes?
Yeah, again, what is our data rate?
1.4 terabytes a night.
1.4 terabytes a night. So it's really not tremendous. That's for the full. No, I mean the modern terminology. That's it. And that's for 331.
That's with the 256 input correlator.
For the 256 input correlator. That's here at 128 then.
Yeah, that'll scale up to that.
All right. So when we get up, we'll go by a factor of a few beyond that. It's not huge. It really isn't. I'm not. Again, that's not something that keeps me up at night.
Sorry. Do you observe in the daytime?
No, you don't want the sun up. And so the idea is we have like a 4-month period where the coldest part of the sky is up, sun is down, et cetera, et cetera. And so there's about 4 months of the year we can observe through the night, right? And that's what we're targeting. I mean, we can observe in the day. It's not as if we keep, but we won't use those data for.
Okay, I'll thank Chris again.